Okay, so as I mentioned, we can write the KSP expression for any ionic compound. And typically what we're going to see is that the ones that we're going to look at involve what are known and sometimes referred to as sparingly soluble salts or sparingly soluble ionic compounds, because their KSP values are generally going to be very, very, very small, right? So they range from 10 to the negative 6, like the one that we looked at, all the way to 10 to the negative 33. That's a really, really, really small value, right? So that aluminum hydroxide really is not going to dissolve to any extent at all. Now, when it comes to describing the solubility or to express the solubility of a substance, there are two general ways to express the solubility, right? How does something dissolve? So one's called a molar solubility, which is the number of moles of solute that can dissolve in a liter of the saturated solution. And the other one is the one we've seen previously, which is just solubility, which is the grams of solute in every liter of saturated solution. So to calculate a substance's molar solubility, we are going to construct a regular old equilibrium table, fill in our what we know, and then determine the unknowns just using basic math and equilibrium principles that we've seen before. Okay, so let's take a look at an example. This is going to be a lot simpler than some of the ones we've seen previously. So let's take a look. So it tells us the KSP for silver bromide. So silver bromide is AgBr. The 7.7 times 10 to the negative 13. Calculate the molar solubility of AgBr, right? So the molar solubility would mean moles of AgBr per liter of solution is what we want to determine. So we have our equation written up here. We have our initial concentration. Okay, we don't know. Well, initially, we don't have any of these things. The change in concentration, we usually call that X. Here, we're going to use S to refer to solubility, just to distinguish it from the X we've seen before. You can use X as well, but S is more appropriate. So then we have our equilibrium concentrations that are S's, right? So when we write out our KSP expression, that would be the concentration of Ag plus times the concentration of Br minus. And then that is equal to the KSP value, which you can look up, 7.7 times 10 to the negative 13. This is S, this is S. So then we have S squared is equal to 7.7 times 10 to the negative 13. So S then would be the square root of 7.7 times 10 to the negative 13. So the S there ends up being 8.8 times 10 to the negative 7 molar. If we were asked to determine the solubility, right, so this here is the solubility, or the molar solubility. Okay, so what this means is that we can dissolve 8.8 times 10 to the negative 7 moles of silver bromide in every liter of solution. We could also convert this to regular old in grams per liter. Okay, because we have our 8.8 times 10 to the negative 7 moles of AgBr per liter. This just involves a molar mass conversion. So for every 1 mole of AgBr, we need the molar mass of silver bromide, which is 8.8. I'm sorry, which is 187.8 grams of AgBr. Okay, so the moles go away. We end up now with grams of AgBr per liter of solution. We evaluate that. That ends up being 1.7 times 10 to the negative 4. Right, so this would be the regular solubility in grams per liter, and we have the molar solubility that we calculated previously. Okay, so this is if we had a 1-to-1 ratio of the ionic compound to the ions that are produced. What if the stoichiometry was different? Okay, so it says calculate the solubility of copper-2 hydroxide in grams per liter. So when you write the dissociation of the copper-2 hydroxide, so CuOH2 solid, okay, this will dissociate to give you the copper-2 plus ion, and then we get 2 hydroxide ions, right? So when we do our ice table, okay, so we're not really concerned about this here. Originally, we have none of this. We're going to get plus S. Now we get plus 2S, right? The stoichiometry is different now. So at equilibrium, we have our values. So when we write our KSP expression, that would be equal to S times 2S is equal to the KSP for copper hydroxide, which is 2.2 times 10 to the negative 20. Okay, so S times 2S is 2S squared, 2.2 times 10 to the negative 20. So then our S would be equal to 2.2 times 10 to the negative 20 divided by 2. And then we take the square root of all of that. Okay, so it's very easy to get confused. When we do this, so let me let you know what that actually means. Because it's very easy to make that mistake, which if you look closely at it, we also made this mistake here. So we want to make sure that we resolve that. So if we were to write again, our KSP, right, is a concentration of the Cu2 plus times the concentration of the OH minus, and now because of stoichiometry, we need to raise it to the power of the stoichiometric coefficient, right? So we want to make sure that we address that. So this will change what our expression is down here. So, so we have our S and then our OH minus concentration, right? That's 2S. And then now that itself has to be squared. Okay, according to the stoichiometry. So we have now our S times 2S squared is equal to 2.2 times 10 to the negative 20. So this ends up being 4S cubed. So you want to make sure that we keep track of the stoichiometry in the equation, but also when we write that KSP expression, we need to incorporate any of those coefficients as superscripts, right? So we have S times 2S squared is equal to KSP. So 4S cubed then is equal to the KSP value. So our S actually now is equal to the 2.2 times 10 to the negative 20 divided by 4. And then we're going to take the cubed root of this. So our solubility here ends up being 1.8 times 10 to the negative 7 molar. And then if you want the solubility in grams per liter, we would take this and incorporate the molar mass. So for every 1 mole of the copper hydroxide, right, we calculate the molar mass 97.57 grams. And then we end up with the molar solubility there being 1.7 times 10 to the negative 5. I'm sorry, the solubility in grams per liter is 1.7 times 10 to the negative 5 grams per liter. So the moral of the story is when you write your expression and you dissociate the compound into its ions, pay attention to the stoichiometry, and then when you write your KSP, make sure you incorporate any of those coefficients as superscripts, and then we can solve for the unknown. Now, by the same token, what we can do is we can work backwards. If we're given the solubility of a compound, we can work backwards and calculate the KSP, right? So if we have our calcium sulfate in this case, okay, this would give us our calcium ion, and then we get the sulfate 2 minus. So then our KSP here would be the Ca2 plus times the SO4 2 minus ion. And we're told that, so if this is S and that's S, so our S squared is equal to our KSP. Okay, so we need to know what S is. And we're told here that the solubility is 0.67 grams per liter, and that's of the calcium sulfate. Well, S here is the molar solubility. So this we need to convert it to moles. So for every 1 mole of CaSO4, we have 136.2 grams. So the grams go away. So we end up here with 4.9 times 10 to the negative 3 molar, right? And that is our S. So we can take this, we can substitute it into our equation. So we end up now with our KSP being equal to 4.9 times 10 to the negative 3 squared. And that is going to give us 2.4 times 10 to the negative 5 for our KSP, right? So going forward, in the forward direction, we can determine S, the molar solubility, or the solubility in grams per liter. We can also go backwards as well. In the reverse direction, determine KSP if we're given the solubility or the molar solubility.